Welcome back to The Explainer. Today, we're cracking open a case file from a recent linear algebra exam, specifically question 6. It's this awesome two-part mystery that's got a vanishing variable, a potential secret identity, and a really deep abstract truth at its core. Okay, let's get into it. So, meet our two main players, matrix A and matrix B. As you can see, they look pretty complicated, and their properties are all tangled up with this one mysterious variable, A. Our mission is to figure out the relationship between these two. The first part of this mystery is a classic identity check. We need to find out for which values of A these two matrices have the exact same determinant. Think of it as their unique DNA marker. This is our first big clue in the investigation. All right, to solve this, it's time to do a little forensic work on the matrices themselves. We're going to start by calculating their determinants, which is like finding a unique numerical signature for each one. This should give us our first solid lead. Let's start with matrix A. Now the key here isn't brute force, it's about being clever. See that first step? With one slick column operation, we create two zeros in the bottom row. This is a classic linear algebra trick, because, as you can see in step 2, it makes expanding the determinant incredibly clean. And when we work it all out, poof, the variable A just completely disappears.
And that right there is our first major finding. The determinant of matrix A is always -1. It doesn't matter what A is, it's a constant. It's a fixed piece of evidence we can rely on.
Okay, now let's see what happens with matrix B. We'll use a similar trick, this time with a row operation, to get a couple of zeros in the first row. But when we expand along that row, something totally different happens. Unlike matrix A's constant identity, B's determinant is completely tied to our variable A. And there you have it. The determinant of matrix B isn't a constant at all. It's -A squared. The identity of this matrix literally changes depending on what A is. So here's where it all comes together. We need the determinants to be the same, right? We just set them equal to each other. -1 equals -A squared. A little bit of simple algebra, and we've found our suspects. The only two possible values for A are 1 and -1.
But finding when the determinants are equal is really just scratching the surface. Now we get to dig deeper. Could there be a more intimate connection between A and B?
This brings us to the second and maybe more interesting question in our investigation. Could matrix B actually be the secret identity of A's inverse? I mean, if that's true, it would mean they're fundamentally linked.
To answer this, we need to pull out a fundamental rule about inverses. An inverse matrix basically undoes the original, so their determinants have to be reciprocals of each other. That means the determinant of A's inverse has to be 1 over the determinant of A. And since we already know the determinant of A is -1, well, the determinant of B must also be -1 for it to be the inverse.
And hey, look at that. The condition for B being the inverse, that its determinant is -1, is the exact same condition we found in the first part of our investigation. This confirms we're on the right track and lets us focus our attention entirely on our two suspects, A equals 1 and A equals -1. Okay, time for the final showdown. Let's plug in our suspects and check the evidence directly. On the left, we set A to 1, multiply A and B, and boom, it's a perfect match. We get the identity matrix. But on the right, when we try A equals -1, the multiplication goes wrong right out of the gate. That 7 in the corner tells us everything we need to know. It's a definite no-go. The evidence is conclusive. Only one of our suspects is the real deal. It's only when A is equal to 1 that B is the inverse of A. And with that, Act 1 of our mystery is solved. But hold on. Our case isn't over yet. We're now moving from the world of concrete calculations to a much more profound abstract puzzle that really tests the fundamental principles of linear transformations. So here's our next challenge. It's a theorem. A universal statement about some linear transformation we're just calling T. I know it looks dense, but don't worry, we're going to break it down piece by piece.
First things first, let's define our terms. What is the kernel of T? Well, you can think of it as the null space. It's basically the collection of all the input vectors that get completely squashed down to the zero vector by the transformation.
Now that condition we're given, it looks super intimidating, right? But all it's really saying is that the outputs of T, which we call the image, have nothing in common with the vectors that T squared sends to 0, except for the 0 vector itself. There's no non-zero overlap between them. That's it.
So how on earth do we prove this thing? We can't just plug in values like we did before, because this has to be true for any transformation T. Instead,
We have to use the pure logic of vector space dimensions. This is going to be our final deduction.
And here are the tools we'll use for this last part of the investigation. First, a basic property. Anything that t sends to 0 will definitely also be sent to 0 by t squared. Then, we bring out the big guns, the dimension theorem for sums, and the famous rank nullity theorem.
Okay, follow the logic here. First, that given condition about the zero intersection lets us use the dimension theorem for sums, which gives us the inequality you see in step 1. Now just hold that thought and look at step 2. The rank nullity theorem gives us a hard and fast equality. Now, if you compare step 1 and step 2, they're almost identical. And that forces the conclusion in step 3, the dimension of the kernel of t squared has to be less than or equal to the dimension of the kernel of t.
And this is the brilliant final move. It's a dimensional squeeze play. We already knew from a basic property that the dimension of ker t is less than or equal to the dimension of ker t squared. But we just proved that the opposite is also true. We've got it trapped from both sides.
When a number is both less than or equal to and greater than or equal to another number, there's absolutely no wiggle room. They have to be the same. The dimensions of these two kernels have to be exactly equal. And this is the final piece of the puzzle. We know one kernel is a subspace of the other, and we just proved they have the exact same dimension. In the world of linear algebra, that means they have to be the exact same set. The proof is complete, and our case is elegantly and definitively closed.